Hi everyone, welcome back to our series. My name is Zafira Gimbatin, and today we will be going over thermal performance testing and measurement in semiconductor packaging. In this presentation, we'll explore the fundamentals and importance of thermal testing and semiconductor packaging. We'll begin with a brief introduction and discuss why thermal testing is so critical in ensuring the reliability and performance of modern electronic devices. Next, we'll define the key thermal parameters and metrics that engineers use to characterize heat transfer and temperature limits within semiconductor components. After that, we'll review testing techniques and specific methods for measuring junction temperature, followed by an overview of infrared thermal imaging and how it's used to visualize and analyze temperature distribution. We'll also look at thermal test die calibration, thermal resistance measurements like R theta JA, R theta JC, and R theta JB, and how power cycling and thermal shock testing reveal long-term reliability. Moving forward, we'll cover dynamic thermal characterization, real-time sensing techniques, and how data is processed through signal acquisition systems and test equipment setup. To tie it all together, we'll examine two case studies, one-on-one power module thermal validation and another on high-frequency RF device testing. Finally, we'll close with a summary and discuss emerging trends in semiconductor thermal management and reliability testing. Before diving into the testing methods, let's start with why thermal performance is so important in semiconductor packaging. Every electronic device generates heat during operation, and the semiconductor package has to dissipate that heat efficiently while still protecting the internal components. If heat isn't managed properly, it can lead to performance degradation, instability, or even device failure. That's why thermal testing is a critical step. It verifies that the thermal design of a chip or module actually meets its performance and reliability targets under real operating conditions. Accurate temperature measurement is also key. It allows engineers to identify thermal bottlenecks, validate heat-spreading materials like thermal interface materials, and optimize cooling solutions such as heat sinks or advanced packaging designs. The diagrams on the right show a basic heat dissipation path from the chip through the thermal interface material to the heat sink, and how more advanced multi-chip packaging integrates stacked layers for improved power density but also great thermal challenges. Thermal performance plays a major role in device reliability, efficiency, and lifespan. As semiconductor devices continue to shrink in size and increase in power density, managing heat becomes one of the biggest challenges in packaging design. When junction temperatures rise too high, they accelerate wear-out mechanisms such as electromigration, die cracking, delamination, and material fatigue. Over time, these effects can cause permanent damage and failure, especially under repeated thermal cycling. The diagrams on the left illustrate how thermal stress builds within the package. Elevated temperature and moisture can cause vaporization and pressure buildup during reflow, leading to package deformation and eventually cracking. The thermal map on the right shows an infrared temperature profile of an operating module. The red regions indicate hotspots, revealing how heat is distributed across the package. This is exactly why thermal testing is so important. It allows engineers to evaluate how effectively heat moves through the device, identify weak points in the thermal path, and ensure the package performs reliably under real-world operating conditions. Now that we've discussed why thermal testing is important, let's look at the key parameters and metrics that define thermal performance in semiconductor devices. The first and most critical is the junction temperature, denoted as T sub J. This is the temperature at the semiconductor die, and it directly affects the device's electrical performance, reliability, and lifetime. Keeping the junction temperature within safe limits is essential to prevent damage or accelerated aging. Next are the thermal resistances, R theta JA, R theta JC, and R theta JB, which describe how efficiently heat moves from the junction to the ambient case and board, respectively. These parameters help engineers quantify how well heat is being transferred out of the device. The symbol change in T Delta T represents the temperature difference or gradient across different layers of the package, which helps identify where thermal bottlenecks might occur. Finally, thermal time constants and transient responses describe how quickly a device's temperature changes when power is applied or removed. This is important for understanding dynamic heating behavior during switching or power cycling. On the right, you can see the heat dissipation paths from the die through the exposed pad and copper layers. The graph on the left shows how the total thermal resistance decreases as the heat spreading area increases, demonstrating the impact of layout and material choices on cooling efficiency. There are several techniques used to evaluate the thermal behavior of semiconductor devices. The two main approaches are steady-state and transient thermal testing. Steady-state thermal testing is used to determine the baseline thermal resistance once the system has reached equilibrium. It helps engineers understand the constant heat flow from the junction to the ambient environment, giving an accurate measurement of overall thermal efficiency. On the other hand, transient thermal testing focuses on how the device responds to changes in power over time. For example, during power cycling or dynamic load conditions, this technique reveals how fast heat builds up or dissipates, and helps identify short-term thermal bottlenecks that steady-state tests might miss. Finally, calibrated thermal test dies often are used to ensure consistent and repeatable measurements. These specialized dies have built-in temperature sensors and known power inputs, allowing researchers to precisely characterize the thermal path under controlled conditions. The images shown here illustrate some of the equipment used in these experiments, from full-scale thermal laboratories to environmental chambers that control temperature and humidity for reliability testing. Measuring junction temperature provides insight into how a device performs thermally at its core. Embedded thermocouples, or diodes, can directly measure die temperature, while electrical testing methods use voltage changes to infer it. Infrared thermography captures surface temperatures non-invasively, offering a full visual map of heat distribution. Together, these methods help engineers monitor both internal and external temperature behavior. Infrared thermal imaging allows engineers to visualize heat flow and temperature gradients in real time. High-resolution IR cameras capture even small variations, while analysis software identifies hotspots and inefficient heat paths. The images shown here illustrate how thermal mapping is used for dies, PCBs, and power modules to verify and improve cooling designs. To ensure accuracy and repeatability in thermal testing, engineers use thermal test dies and calibration standards that replicate the behavior of actual semiconductor devices. A thermal test die includes a precisely controlled heating element and integrated temperature sensors, allowing for consistent power dissipation and accurate temperature measurement across multiple experiments. These dies serve as a reliable reference when evaluating different cooling solutions or package materials. Standardized test packages are also used to compare thermal resistance across various designs and manufacturers. This helps maintain consistency when reports resulting such as R theta JA, R theta JC, and R theta JB. Calibration is critical. It ensures that different instruments and setups yield comparable and trustworthy data. In practice, calibration often involves aligning IR camera readings, verifying laser alignment, and validating heat distribution across a controlled target surface. The images here show a laser-based calibration setup. In Figure A, a laser collimator and a beam expander generate a uniform heat zone on a copper strip. Figure B shows the actual setup, and Figure C displays the thermal image, highlighting the radiated and measurement zones used to verify system accuracy. Together, these methods establish a reliable foundation for all subsequent thermal testing and characterization work. Thermal resistance testing measures how efficiently heat moves from the chip's junction to the ambient environment. R theta JA, R theta JC, and R theta JB define the main heat paths through air, the case, and the board. The graph shows how temperature difference changes with power, providing insight into heat transfer efficiency. Controlled airflow, ambient temperature, and power input are essential for reliable test results. Power cycling repeatedly heats and cools devices to test material fatigue and long-term stability. Thermal shock testing exposes components to sudden temperature changes, identifying weaknesses like cracks or delamination. Specialized test chambers maintain strict thermal control, ensuring accurate, repeatable results that reflect real-world conditions. Dynamic thermal characterization focuses on the transient behavior of semiconductor devices, how temperature changes over time when power levels fluctuate. In this method, devices are subjected to rapid power pulses, allowing engineers to observe how quickly heat is generated and dissipated. These short bursts simulate the switching conditions found in real electronic systems, such as power converters or RF amplifiers. By measuring how temperature rises and falls during these pulses, researchers can determine the thermal time constraints of the device. These constants describe how fast the device responds thermally to process changes and help model transient heating effects. The schematic on the left shows a typical test setup using an arbitrary function generator, gate drive circuit, and oscilloscope to control and monitor voltage, current, and temperature in real time. The plot on the right shows temperature versus time at different load conditions. Each curve represents a distinct operating power or ambient temperature, illustrating how thermal response varies with load. The data gathered from these tests is critical for predicting junction temperature under dynamic operating conditions, ensuring that devices remain reliable even under fast switching or high power transients. Real-time sensors provide continuous temperature feedback during testing or operation. Devices use thermocouples, RTDs, thermistors, or digital sensors connected to data acquisition systems. This enables live temperature monitoring and automatic control, critical for ensuring stability in high-performance electronics. Data acquisition systems, or DAQs, collect and process thermal signals from multiple sensors simultaneously. Signal conditioning removes noise and amplifies weak inputs, improving accuracy. Real-time software then logs and visualizes the data, allowing engineers to interpret temperature trends and make informed design adjustments. To demonstrate how these thermal testing methods are applied in practice, let's look at two real-world case studies. The first case focuses on power module thermal validation. Here, the goal was to measure R theta JC, or the thermal resistance from junction to case, using a calibrated thermal test die. The module was subjected to power cycling under controlled ambient conditions to evaluate temperature stability. By monitoring the junction temperature over time, engineers were able to confirm that the device maintained thermal equilibrium during continuous operation. Verifying the effectiveness of the heat dissipation design, the cross-sectional diagram on the left illustrates the thermal path from the chip through the solder layers, baseplate, and heatsink. The second case study examines high-frequency RF device testing. In this setup, infrared thermal imaging was used to visualize temperature rise in an RF power amplifier during high-frequency switching. Thermal maps, like the one shown on the right, reveal how localized heat spots form in an amplifier module during operation. This data allows engineers to optimize the cooling layout, refine material interfaces, and ensure stable operation under high power density. Together, these case studies highlight how thermal testing bridges design and reliability, providing essential feedback for improving next-generation semiconductor packages. In summary, accurate thermal measurement is essential for designing reliable semiconductor devices. Thermal testing helps validate both steady-state and transient performance, ensuring that heat is managed effectively under real operating conditions. Looking ahead, we're seeing major progress with integrated thermal sensors, machine learning for predictive analysis, and advanced data acquisition systems for faster, more precise testing. Cooling innovation is also moving forward, from liquid-cooled lids to direct die and in-chip cooling, all aiming to lower thermal resistance and improve efficiency. Together, these advancements are shaping the future of thermal management and enabling the next generation of high-performance electronics. Thank you so much for watching. We'll see you again in the next video.